No. Anyway, again, I'm very happy to be here meeting the representatives from the 4 countries as well as the different partners in this project, including those from JAXA and RESTEC. I'm learning myself some details about the front end of the methodology in terms of developing the sampling frame. So this was a very valuable introduction before we get into the sampling aspects. So during this presentation, we're going to be talking about the overall objectives of the pilot rice crop cutting surveys and the 4 provinces and the 4 countries of Southeast Asia, and the sampling frame for the surveys, and how we stratified the survey. That's a lot of that is related to what we heard this morning about the INAHOR and the application from RESTEC. And we're going to take a look at the distribution of the meshes by stratum for each pilot province, and talk about the sample design for the pilot surveys. And we'll look at the sample size and allocation, and see how the meshes are distributed by stratum. Then we're going to talk about rice area estimation, the weighting procedures, how we would estimate the average yield of rice from the crop cutting data. And then we're going to look at a ratio estimation of total rice production of rice paddy that can be used to improve the precision of the estimates. And in order to evaluate the precision of these estimates, we're going to take a look at sampling intervals, confidence intervals, design effects, some statistical aspects of showing the efficiency and effectiveness of the sample design. We're going to compare the different results in order to draw conclusions and have some brief recommendations. So Nagraj had already described a little bit this morning about the different available sources of information on rice crop area and production estimates. And most countries have some types of administrative reporting systems. And typically, a Ministry of Agriculture will have a extension program. And I've been working this year recently with BPS in Indonesia. And they work with the Ministry of Agriculture there in producing estimates for different crops, including rice production. And they have a estimation that starts at the district level with the extension agents using what they call an eyeball method, okay, and taking a look at getting a general estimate of the crop area, and they may do get some local information in terms of estimating the yields also. And in the end, they come up with estimates of the crop production in each of the districts that's summed up to the province level and then the national level. And it turns out that these results are very biased. For one thing, as Nagraj pointed out, the people producing these results have an interest in showing that they are doing a good job in increasing the production. And so the total production seems to be generally overestimating the production in rice and other crops. And BPS is starting to introduce an area frame for rice that also based on satellite image, but it's just at the pilot stage right now. You just heard about the satellite data method using INAHOR and the application from RESTEC. And that's another source. And of course, that also needs to be validated. And you heard some results that this morning. And finally, there are household surveys that many countries rely on that are based on either farmer recall or crop cutting. And we'll see in the presentation this morning that crop cutting is a way of what we call ground truthing the yield data in order to validate the yields eventually produced by the RESTEC methodology. It's important to have ground truthing, so the crop cutting is also important for that purpose. And so we're going to be focusing on the crop cutting survey and also a farmer response survey that was conducted under the project. And so it is very important to ground truth the information, the estimation from the satellite data, and also take a look at the cost effectiveness as was discussed just now. And so the benchmark estimates from the crop cutting will help to determine if there's any bias. And well, of course, different methods have different sources of bias, so we have to compare these in relative terms in terms of evaluating the results from each source. Now, there are two types of frames that are generally used for agricultural surveys. And the first method that's used by many developing countries especially is a two-stage list frame. And where typically a census frame is used at the first stage, where the country is divided into segments called census enumeration areas. And that's a population-based frame, but in rural areas where most of the households are involved in agriculture, that's sometimes used as a frame for selecting households with agricultural operations. And then you go to the household and ask about the plots owned by the households, in this case where rice is grown. And then you obtain either crop cutting or farmer recall data. In our case, we did both. And that data is used then based on statistical methods for weighting, for expanding the data, and coming up with results. Now, the INAHOR and RESTEC methodology was typical of what we call an area frame, where typically you use remotely sensed data, as we saw this morning, to classify the land into different types of land use. In this case, the growing of rice on in the areas to identify which areas rice is concentrated in. So that's used for the stratification. And then once we'll take a look at this stratification in more detail. But within each stratum, then, we select a sample of areas that was referred to as meshes in this case, which is 200 meters squared. And then we go to each of these meshes, sample meshes, to list all of the rice plots that have some rice growing in them. And we select a sample of plots. Then finally, we select a subplot for doing crop cutting. So we're going to talk about this methodology in more detail. But as a general background in terms of enumeration under area frames, there are two different approaches. that are used for agricultural surveys based on area frames. The first approach is called the closed segment enumeration. And in the case of closed segment, you account for all of the land that's within the boundaries of your mesh or sample area. And then the area and production of the crops for all plots inside the boundaries are enumerated regardless of where the farmer actually lives. So all you're looking at is the land that falls within the area of the mesh. Then the estimates of area sometimes are based on objective area measurement, or they can be used by GIS tracking, as in the case that we'll be discussing this morning. Okay, now the other type of enumeration is called open segment enumeration. And this is where you identify the farm households that are located inside the boundaries of the sample segment. And when you're looking at farm level characteristics, sometimes this is approach is needed. So you can ask about not only the plots inside the mesh, but farm level characteristics. Now, the two-stage list frame that I was mentioned before is designed specifically for this open segment approach. And because it's actually population-based, and you control, enumeration areas control how many households you find in segments, whereas the area frame controls the area that you want to cover. And so both of these have their own uses. And, but in the case of our survey, we actually had what we're going to call later is a mixed or weighted segment approach, where in the farmer recall data survey, we're asking about the information for the entire farm, and we're going to be reviewing that also. And actually, we can take a look at, okay, the closed and open segment approaches here in terms of a mesh. And so this is the same mesh that was referred to this morning in discussing the ResTech methodology. So the red there marks the boundaries of the mesh. And for the closed segment approach, you would be accounting for all of the land area within this segment. Now, outside of rice production, and some countries, including the US, they use area frames to look at crop area and production for all different types of crops. And the way they do that is to account for every piece of land in there. And they also stratify by land use, but for a variety of crops, not just for rice. And in terms of the open segment, you see that there are only a few structures in here where some farm households may be living. So you can see that since this is an area-based frame, you're going to have a large variability in the number of households that you would find in a particular mesh. And so this is what the typical 200 by 200 mesh looks like in terms of the area on the ground. Now, stratification, of course, is a very important aspect of sampling to make the sample design more efficient. And so this is the key in coming up with an effective sampling strategy for the rice crop cutting survey. And so we have 4 different strata that were used to identify, based on the satellite imagery and the ResTech, Inahor ResTech methodologies you saw this morning. They were able to divide the whole area of each of the 4 provinces into these 4 strata. And just quickly, in terms of the first strata, you have maps obtained by IRRI, based here in the Los Baños, using 215 MODIS data and from land use maps produced by the European Space Agency under its Globe Cover initiative. And anyway, this was used to identify the extent of rice growing in the different selected provinces. Okay, so this is the stratum that has the highest probability of finding rice. So basically, we want to divide the territory of each province into areas based on the concentration of rice. And since these were identified as rice by both IRRI and Globe Cover, there's a high probability that you would find rice there. The next stratum was areas identified only on the IRRI area maps. So these were overlaid, and you found which areas were identified as rice, covered with rice in both IRRI and Globe Cover. The other was only in IRRI, and the third one were areas identified only by Globe Cover as having rice. So these have a smaller probability. And finally, to make sure that we have complete coverage, we identify the rest of the province as other, okay. And this would include urban areas, forest, lakes, areas covered by water, and this has a very low probability, but still we want to make sure that we have a probability of covering any rice that is grown in each of the provinces. Okay, so after the process that you saw this morning with Inahora and Restic, the territory of each of the provinces was divided into these meshes of 200 by 200 meters squared. And so this is the distribution in each of the provinces in terms of the 4 different strata. And here you can see the total number of meshes in each of the provinces. So you can see that Savannakhet in Lao PDR is much larger than some of the provinces in terms of total area. So this is just the total area in each of the provinces. And you can also see the distribution varies a lot in terms of the different strata. And so you find, for example, that in the Savannakhet, you have a relatively small percent in IRRI Globe and a larger amount in Globe, but most of the area is covered by other. And we're going to see the maps just now, which illustrates that. Whereas in Angtong in Thailand, for example, you have very little in other, so most of that province is covered, has some chance of having rice grown. So we'll move along here. Now, the first step we had was to allocate the sample of 120 meshes to the different strata. And of course, you want to concentrate your sample in strata that has more rice. And so this was how we designed the sample in terms of dividing the sample meshes to the different strata. And so our basic sample was to cover 80 in IRRI Globe Cover, 20 in IRRI, 15 Globe Cover, and 5 in other. And you can see these are based on the probability that we'll find rice in those particular areas. And we had a uniform design. Since this is a pilot, we had a uniform design for all of the 4 provinces. And then we had replacements in case some areas could not be reached. And so this was a total, but actually the basic sample was 120 meshes for each province. Okay, now this is very interesting. After the process of overlaying the satellite images and stratifying the data, we have here maps of the strata for each of the 4 provinces. So remember when we talked about Savannakhet and Lao PDR, most of the area was covered in other. So you see all of the purple here covers most of the province. And globe cover, globe plus Erie is the green, and you can see their patches here. And globe cover, you see, has a lot more area outside of the overlap of globe and Erie. And finally, you have very small pockets of area that was only identified as riceland in the Erie stratum. So, okay, so that's Savannakhet. Then we have here Nueva Ecija here in the Philippines. And this is interesting in that other is very sparse here. So the province is highly covered by rice. And the globe Erie covers a good portion of that. But then globe cover covers an additional large portion. Remember, the globe cover actually covers both the blue and green, since this was an overlap. That's Nueva Ecija, okay. And here's Ang Thong, Thailand. And you can see that most of it is globe Erie with some pockets of globe cover, small pockets of Erie. And the other here is hard, even hard to identify, but there was very a small area covered by other. And finally, Tay Binh and Vietnam. You see the other is all mostly concentrated along the edge here, but most is covered by globe plus Erie and some pockets of globe cover, and Erie seems to have small pockets where things were only identified by Erie. So, okay, so that gives you an illustration of the difference of the different 4 different provinces in terms of the coverage by stratum. Next, I want to briefly talk about the different stages of sampling that we used for the rice crop cutting survey. And we just talked about the first stage of selection, where sample meshes are selected within each stratum. For example, 80 were selected within the Erie globe stratum, as we saw in the distribution. So those were randomly selected using a GIS program, okay, within each of the within each stratum. And then the second stage, after the first stage, then they visited all of the 120 meshes to identify, to verify that they actually were growing rice. And it was found that some of the sample meshes did not have any rice growing that season, okay? And we'll see the distribution later of those that had rice. But once they verified that there was rice, then it was necessary to do a listing in each of the sample meshes to identify all of the sample plots and those plots that had rice. So then among all of the plots with rice, they selected a sample of 4. If there were 4 or more, they selected 4. And of course, if they're less than 4, they just selected all of the plots with rice, where even part of the plot falls within the segment. And we'll see an illustration of that. And finally, in the third stage, is where the crop cutting was done. Within each of the 4 sample plots, we'll see an illustration of that also. They went randomly into a 2.5 by 2.5 square meter subplot, and that's where they did harvested the paddy for the crop cutting, and we'll take a look at that also. So those are the 3 stages of selection. Now, in terms of the second stage, we talked about identifying the plots with rice. Now, here are a couple of different examples, okay? Here is your sample mesh, 200 by 200 meters squared. And then they actually listed, well, using an iPad tablet, okay, they had the image, okay, of the mesh, and using that as a guide, they did a sketch map of all of the plots where part of the plot fell within the sample mesh. And then they identified whether each of these had rice or not. So you see in the first example here, they identified a total of 9 plots that fall at least partly within the mesh. And out of these 9, you have 7 that were identified, sorry, you have a total of 8 that were identified with rice. You can see in the case of 9 here, it was all housing units, so it was part of a village, so there was no rice there, but there were rice in the other 8 plots. Here's another example, okay, with the mesh. A total of 7 plots were identified that were partly in the mesh. And out of those, only 3 were found to have rice, okay? So the ones that are circled were found to have rice. The others were, did not have any rice growing. So in this case, we selected 4 out of 8. In the other case, we selected all 3. And this is the sample plot that was measured. The plot was measured, the full area of the plot was measured, as well as the area inside the plot and the area of rice inside the plot. And we'll see how that was used later in the estimation. Okay, and here's an illustration of stage 3. Okay, here is the sample plot, okay, with, that partly fell within the mesh. Okay, and they selected a random number. They measured the two sides of the mesh, and based on a random number, they entered into the mesh, random number on both sides. They entered a random point, and then based on that corner, they had a 2.5 by 2.5 square meter instrument, tool, that they used to put over the rice that was harvested. And we'll see an illustration of that. Okay. Now, why do we use crop cutting? Now, it's a method of a method of objectively measuring the yield by actually harvesting a portion of the plot where the size is very well controlled, and also it's randomly selected so that it is representative. And then the rice that is harvested from that plot is then measured, weighed, and then that is used to measure the yield. Now, the advantage of this is if it's done properly, okay, if it's done correctly, it should be unbiased, reliable, and it's also a probability sample, so we can estimate the sampling error and confidence interval. And you have quality control to make sure that the measurement errors are minimized. Of course, bias can be introduced, okay, if some of the techniques are not done correctly. In terms of the disadvantages, we were talking about cost effectiveness. It is expensive, okay, and that's why the sample that's used for crop cutting is generally small. And of course, you need time to collect the data, do the harvesting and weighing and analyzing the results. So in terms of comparing it to the satellite estimation of yield, of course, it's going to be more expensive, but actually it's used as a part of the validation process, ground truthing the yield that can be estimated more cost effectively using directly the satellite image data. So again, quality control is very critical in terms of ensuring that there's as little bias as possible introduced. And we're going to take a look at the sampling errors later. Now here is a very good illustration of the crop cutting method, and we can go through this quickly. And starting with the selection of the 120 meshes, okay. Then we saw the random selection of plots within each mesh. Here's the tracking of the plot boundaries to get the objective area measurement. Here's the instrument that's used for the 2.5 by 2.5 square meter subplot that's used for the crop cutting. And then once that subplot is harvested, then there's a threshing, cleaning the samples, moisture reading and weighing of the samples, drying through parching, and the weighing and moisture reading of the dry samples. Of course, the moisture reading is very important to make sure that you have consistent state of the paddy that's being measured in order to get accurate estimates of yield. So this goes through all of the steps there. And now I mentioned that one of the first steps involves going over the, visiting each of the rice plots, the meshes, to verify whether or not they have rice. And remember, we selected 80 meshes for the Erie globe cover stratum in each of the provinces. And this is the number of plots that actually had rice. So you see, just because it's stratified as having rice doesn't mean that when you go there, you will actually find rice planted in that season. It could be that that particular season is fallow. It could be that they converted the land use. There could be different reasons for that. And, and the results varied a little bit by stratum, but by province. And now, one interesting thing you see here, remember the other stratum had a very minute chance of finding rice, okay, very low probability. But in the case of Lao PDR, by chance, two of the meshes, we found rice, okay? And actually, those were selected with a very low probability, so they would have a higher weight, which added to the variability. And we'll see that in the results. But in the others, no rice was found in the other, as you would expect. And so the results varied a little bit by province. And you can take a look at this in more detail. Yeah. Okay, thank you. Okay, so we want to move along here and allow some time for questions also. But I wanted to talk briefly about the Farmer Recall Survey. And the crop cutting is what we call an objective measure of yield. And, but typically, in many countries, they still rely on farmer recall for getting both the area and the production of rice. So we wanted to compare what the farmer would tell us was the area in production to what we measured through crop cutting and objective area measurement. In addition to that, we wanted to analyze different characteristics of the farm households. So they collected information on the household, agricultural methods, inputs and sales, farm labor, agriculture extension. And these are very critical parts of information that's needed in terms of developing programs and policies, because just knowing what the yield is, it isn't going to tell you what produced that yield, what the problems were that increased or decreased the yield. So it's very important to have farm level data also. And also we could compare the results to the objective area measurement. And so in this case, we collected data on all of the plots of the farmer. Okay, now we use different methods to measure the area of the plots. And these gave slightly different results, okay? Now in the field listing operation, they did tracking. They actually went around each of the plots and did a tracking with a GPS in the iPad. And so they got the tracked area based on the field operation. And then we got another measure of the area with digitized tracks using Google Earth mapped rice plot boundaries from recent Google Earth images that corresponded to this season. So, and we compared these in the papers that are being written for each country. We compare these different estimates to see what the results would give us. And in the end, we concluded that the digitized tracks probably is giving us more accurate data because you can control a little better the measurement. But finally, we determined the area in rice within the entire mesh by using this Alice method. And so they used the information found during the field validation, and they looked at all areas with rice within the 200 by 2 in the mesh. And these rice areas, all of the rice areas were measured inside the mesh, were measured using the Google Earth method. And actually, since there's no sampling within the mesh, this gives us a more precise and more accurate estimates of the total area in rice. And this was used later, as we'll see, for estimating for a ratio estimate of total rice production that gives us a more accurate figure. And so anyway, this was the Google Earth image that was used in terms of the actual measurement. And if you have any further questions about that, I'll ask the team here. Now, in terms of estimating the area inside the mesh, They use the Quantum GIS, or QGIS, which is an open source GIS application that provides viewing, editing, and analysis capabilities. So that was done here at ADB to get the total area of rice in the mesh. Okay, now that we've obtained these data, how do we make estimates? Okay, how do we get unbiased estimates from the crop cutting data that we obtain? Of course, we have to respect the sample design and look at the probabilities at each stage of selection, and then the inverse of the probabilities will give us the weights. So let's take a look at the different probabilities. At the first stage, we have the denominator here is the total number of meshes. So we're simply taking a sample meshes out of the total number of meshes in the frame. For example, in the case of the Globe Erie stratum, we're selecting 80 out of the total number of meshes in that stratum for each province. So that gives us the first stage probability of selection. Of course, this was vary by stratum, and the other stratum, for example, we were only selecting 5 sample meshes, so this probability is going to be fairly low. Okay, at the second stage, we generally select 4 sample plots out of all of those that were identified in the listing within the mesh. So any plot that had even a small part area inside the mesh was given a chance of selecting. And we selected 4 of those, as we saw in the previous illustration. And capital N is the total number of plots that are at least partly within the mesh. So again, that was based on a simple random sample. So it's just 4 out of the number that were listed. Now, at the third stage, remember, we're selecting a subplot within the plot with rice. So we randomly go to the point where we find that area, and that area is 6.25 square meters. So the probability of the third stage is just the size of the subplot divided by the size of the entire plot. Okay. So this gives us the third stage of probability for the crop cutting data. Okay. Now, how do we calculate weights from these probabilities? Okay. First of all, we can look at the weight of the sample mesh. It's just simply the inverse of the probability, okay, which is the total number of meshes divided by the sample in each stratum. And in the case of the second stage weight, we have 1 over the first stage weight times the second stage weight. And we saw those probabilities before, so it's expressed in the terms of the first stage, the second stage. Now, then we have to take into account the area inside the mesh. And why is that? Okay. Now, in the case where part of a plot is in one mesh and part of it is outside, it means that that plot could be selected in either of the 2 meshes. Okay, so it has a multiple chance of being selected in any mesh where it is found. So in order to avoid the duplication in the weights, you need to adjust it by the area, area of the plot that is inside the mesh, the proportion of the area that's inside the mesh. So this is the weight of the full plot. Okay. And so this is what was used for the plot level data. Okay, and here's a good illustration of different situations that we would find. In this case, the entire area of the plot is inside the mesh. So in this case, 100% of the area is inside the mesh. So that factor was 1. In this case, you have part of the mesh, part of the plot is inside the mesh, part of it is outside. And so the intersect is the part that's inside here. And that was used to adjust the weight. And again, QGIS was used to measure the area intersect of the part that's inside the sample mesh. And so when we look at the actual crop cutting data, okay, the weight of the rice that was harvested in one of these 2.5 by 2.5 square meter subplots, this would be the weight. So this is a weight of a single subplot where we're doing the crop cutting. And again, we're just multiplying the 3 different probabilities and taking the inverse of that. Okay, so this is the overall probability, and we're taking the inverse to calculate the weight. Now, in the case of the farmer recall survey, the weighting, some aspects of the weighting are similar, but some of it is slightly different, okay? Now, because we're getting information for the entire farm, okay? Now, for the crop cutting, for the farmer recall survey, we are interviewing each farmer who had a plot selected, okay? So we're going from the 4 sample plots to find the farmers. So we have to find out what is the probability of the farmer being selected so that we can calculate the proper weight. So we have the first stage of selection of the mesh, the second stage, probability of selecting the subplot. But in this case, we're asking the farmer not only about the plots that partly fall inside the mesh, we're asking the farmer about all the rice plots, okay, about all of their plots. So in this case, the numerator here would be the area of plots planted in rice inside the sample mesh, okay, as before. But this is for all plots, for not only those that are selected. Some of the plots may be inside the mesh, but they were not selected. But this is all of the plots of the farmer. So we're talking about his entire farm, okay? And the denominator is the area of all plots regardless of where they're located. They may be located entirely outside the mesh, okay? So anyway, this is the probability, that this weight is based on the probability of the farmer being selected for the survey. And this is what we call the weighted segment estimation procedure that I mentioned before that's used for open area segment approach. Okay, now how do we estimate the actual yield of, in terms of kilos per meter square, okay? Now, we saw the weight of the subplot previously, okay? So we use that weight and multiply it by the kilos of rice that were rice paddy that were harvested in that particular subplot. So it's the weight times the production in the subplot. And so the numerator of the ratio is the total production. This is a direct estimate of the total production. And the denominator is the estimate of the total area. And remember, we calculated the area from the plot level data, but you could also calculate it from the subplot level, because the subplot was just another stage of selection. They should give you results that are that are almost the same. So this is the total area of the rice planted in rice, and the numerator is the total production. So we have kilos per meter squared. And this is just based on the crop cutting, the total weight of the rice that was harvested for a particular subplot. Okay, so based on the yield that we get, kilos per per meter squared, we can use the area estimated from the mesh level objective measurement in order to improve the estimate of the accuracy of the estimate of total rice production. So in this case, A is an independent estimate of total area planted in rice, in this case from the mesh level digitized rice area. This ratio estimation is used sometimes when you have administrative information, for example, on total area planted in rice. You could use the yield with any independent accurate estimate of total area in rice. Our most accurate estimate of total area in rice was based on the mesh level digitized rice area. So as we'll see, this gives us a smaller sampling error and also a more accurate estimate of the total rice production. Okay, and as most of you know, we measure the precision by the sampling error, which gives us, which is the variability between the estimates from all possible samples. Every sample will give us a different result. The confidence interval gives us a range of values where, for example, 95% of the estimates would fall. That gives us an idea the true value would be within that range. Now, the design effect is a measure of the relative efficiency of the sample in each stratum. And this is the ratio of the actual variance of the indicator based on the multi-stage sample we used to the variance based on the assumption of simple random sampling of the same size. And so we calculated this also to evaluate the efficiency of the sample. And I'm going to just go through this quickly in terms of the time. Okay, we're doing okay. I want to make sure that we have time also for some questions. Okay, so here are the estimates of total rice area based on, remember we looked at 3 different methods of measuring the area. The digitized GPS tracks were based on measuring the area of the plots in the office, okay, using the Google Earth Maps and the listing information, and which we determine is more accurate than the just the tracking that was done in the field. Okay, so for each of the provinces here, we have the estimates of total area in meters squared, and we have the standard error, the coefficient of variation, our relative standard error, the confidence interval, the design effect, and the number of observations. In this case, the number of observations is the number of plots. Remember, the maximum number of plots would be 120 times 4, okay, but you can see there's less than that for each country, depending on how many of the meshes actually had rice on them. And the first thing we can compare is the coefficient of variation, the relative standard error, okay? You could say, if you change this to percent, this is the percent of error compared to the estimate, okay? And so in the case of Tai Binh, 9.3%, Savannakhet, 16.4%, which is relatively high, Anthong 13.7%, Nueva Ecija 9.5%. Okay. Now remember, this is from the area measured in the plots, okay? Again, from the redigitized track data. So now, what does the design effect tells us? What the design effect is measuring is the homogeneity, the similarity in the size of the plots within a particular meshes, okay? And so you can see this varies also by country. Now, there's going to be a separate report for each of the 4 provinces, and in that report, we'll have detailed information at the stratum level, so you can see where the variability is coming from. But this is just to give you a general overview at the province level for each of the 4. And then if you have questions, we can later we can come back to this. Now, remember, we wanted to improve this estimate by measuring the area of rice, area planted in rice, and the entire mesh, okay, using the Alice method that was described before, where they use the Google Earth map, and they actually measure all of the rice planted inside the mesh, not just for the sample plots, but all of the area. So that means there's no variability within the mesh. There's only variability between the meshes, okay? So this will give us a more precise and accurate estimate of the total area in rice. Now, look at the difference in the relative standard errors. Okay, let me go back here. Okay, take a look at this column here, the CV, and now look at the CV. Okay, so it went from 9.3 to 4.9, and Savannakhet also went down. Some of these went down by more than half. Okay, so this gives us a more accurate and more precise estimate of the total area in rice. And so this is an important part of the methodology for improving the precision of our estimates. And by the way, in this case, the number of observations would be what? The mesh. Okay. So this is actually the number of meshes, because we're measuring the entire mesh in this case. Okay, now I was not involved in some of the other estimates, but this compares the different types of estimates for each of the 4 provinces, okay? And so you can take a look at these results. And in the reports, there's going to be some explanation also of why we find these differences. But it's interesting, when we look at the Inahor AD Restic estimate, okay, we find some differences, more differences here and here, and we can study the reasons for these differences. You find more consistency in the case of Laos and the Philippines in this case. Now, the official statistics come from the whatever source in each of the countries, okay, provides the Ministry of Agriculture or the other source of data for the total area. This is in thousands of hectares, okay, in each of these specific provinces. So this is an important part of the evaluation also. And now this is interesting. We consider that the Alice method will give us more accurate estimates, and you can see that it's giving a much higher estimate in the case of Savannakhet. Okay, we can examine these results a little bit more. Lau PDR was a case where the stratification could have been more effective. Okay, I mean, there were some issues with the stratification. For example, you found 2 meshes in the other stratum that had rice. And we're also finding that in all of the countries, there were a considerable number of meshes that had no rice in the Globe Erie stratum. And so anyway, we'll talk about conclusions later, but you can see that this is something that could use improvement also. So you can examine those results more closely later. Here is a comparison of the estimates of yield in terms of tons per hectare. Before you saw kilograms per kilo squared. Anyway, this is gives you a similar level figure. But anyway, this is from the crop cutting. This is from the farmer's estimate and from the official statistics. And in the case of Tai Binh, you see that there are within a reasonable range. Savannakhet, you see a big difference in the official statistics, and I think there's going to be some discussion about possible reasons for why this was different. Actually, there was another independent estimate, I think, that was closer to the 2.1, 2.3 range, okay. And Thong, the farmer's estimate was higher. And anyway, it's interesting that you've found different results in the different provinces. But, this, we can study some of the causes of this in more detail later. Now, it's important in these estimates also to take into account the sampling error, okay? Remember, these are estimates based on the 3-stage sample. And although the estimates of the yield had a fairly reasonable CV, a relatively small margins of error. But anyway, it's important to take those into account. And in the case of Tai Binh province, these are the estimates of yield in kg per meter square from the crop cutting. And this shows the confidence interval. So in this case, for example, we can see that the yield for Savannakhet and Anh Thong are not significantly different because the confidence intervals overlap a little bit. So we have to keep in mind always that these are samples and subject to sampling variability. So what conclusions do we draw from this study? Now, again, I mentioned that after we did the exercise of looking at which meshes actually had rice growing, we found that a considerable number, even in the Erie Globe stratum where we expected more rice, did not have rice. So there's a need to improve the stratification. It could be that some of the images were older, okay, and we can look at the reasons for that. Of course, you want to use as recent as possible, corresponding to the actual season in terms of the stratification. And also, there's a large variability of plots inside the mesh, and this increases the sampling errors, the variability and the size of the plots, especially in some countries more than others, and that's also discussed in the individual papers. And we also concluded that ratio estimation definitely improves the precision and accuracy of the estimates of total production of rice paddy. So we should continue to use ratio estimation in the context of the rice crop cutting methodology. In terms of the recommendations, the INAHOR AD RESTIC estimates are very important in terms of supplementing the official statistics on paddy rice area, and they can be very cost effective, as we saw in the previous discussion. And each of these methods needs further study, okay, and INAHOR-AD needs to be validated further, and but ground truthing is a very important part of examining potential bias and the accuracy of the satellite image-based estimates. And then the crop cutting is definitely an important tool that can be used for objective measurement of rice yield and production. And anyway, this is a beginning, and I think it opens up a lot of areas for further study also. So I wanted to have enough time for a few questions here. So I'll open it up for any questions you have.